Okay, so we're going to get to more acceleration formulas today. And we have one of them. One of them is actually an old one. A couple weeks back we ran into, but there's, now that we know more about acceleration since back then, like we watched some videos on it the other day, how like some could be, if they're too high, they're deadly and whatnot. But how do you, what are ways to figure them out? And these are probably the four most important equations in mechanical physics, at least for the first part of the year here. There's the main equation is actually this one going back to a few weeks ago. Acceleration is change in velocity over time. And that's actually, that was in words, but in symbols, it's actually this one, just algebraically rearranged. Now, throughout the next couple of days, I'm going to give you a quick proof where some of them came, a lot of them came from. I don't want to bore you too much with that, but I don't want you to think they just came out of thin air. But just a quick kind of review where this one came from, which is actually the same one right here, just rearranged, was from the slope of a velocity time graph when we did those. This one actually comes from a graph too, just some slightly more advanced features of the graph we're not going to worry too much about. And this one comes from some mathematical combining of two of these equations. And I'll talk about this one up here at a later time. But nobody made these up as a point. These are all discovered either graphically or mathematically or a combination of both. Now, to make this as simple as possible, sometimes the algebra could get a little tricky. So what we're going to do today is together we're all going to rearrange all four of these equations. In the past, when I did it on have a hard copy on paper, there was probably enough room in this section to do it because you get right small. But on squid, it would probably just get ugly. So what we're going to do is add pages, okay? I'm going to take all equations, but one thing I'm going to do before we do that, do everything I do basically with me here today. I'm going to number these equations, all right? I'll number them in this order. This is equation 1, this is 2, and there's a reason why I'm going to call this one 3 and this one 4, okay? I know that looks out of order on here, but that's usually the order they're mostly given in, all right? So when I say equation 1, you know which original one I'm talking about when we just move over to another page. So this page 2 on this, we're not even going to worry about right now. So I want you to add a third page. We're going to keep adding a page, and for every equation, we're going to rearrange it how it's necessary. And if there's time today, we'll also get to using some of these. And the thing I'm most concerned with today is algebraically rearranging some of these things. But it's going to be done for you, so as long as you keep this file and save it, you're going to turn it in today at the end just for a few points. So as long as you keep it the next day or two when you work on problems, you just have to line everything up and identify the right equation to use. It'll already be algebraically rearranged if you all follow today. So just make sure you pay attention and write down exactly what I tell you to do. So I'm going to start with equation 1. Now we're going to remember what these variables mean. Many of them we've seen before. So equation 1 looks like this. Df equals Vi plus At. Now, directly, this one's only useful in this form if we're solving for final velocity. So let's just remember that V sub I, that subscript meant what? Because we've found this one in the past. The I means what? If the F meant final, the I meant what? Because when you're accelerating, you're either speeding up, slowing down, and that's all and we know changing direction possibly, but we care about speeding up and slowing down right now. So yeah, initial, right. All right, so a lot of times this equation is called the definition of acceleration. It is the one we found. We're going to solve it in all possible ways. Now, I'm going to talk through it. I'm not going to show every step. I'm going to show the result of every step. Just copy it down with me. So that's the original equation underneath. I'll write it in a different color. All right, if I wanted to solve this for VI, that means isolate that variable. I would subtract over the AT because it's added to it. The main rules of algebra are we can move anything we want to the opposite side as long as we do its opposite operation. So if all this is added, obviously the opposite of add is subtract, right? So if we wanted to isolate initial velocity, it would be Vi equals Vf minus At. If we wanted to solve for acceleration, we put it right underneath this. We'll just go from the top one again. That means get A by itself. I would have to subtract over Vi and divide by T if I followed my rules of algebra. Again, there will be simple equations you guys will be responsible to rearrange here at times, but for the kinematic equations, this is all going to be done for you. You just have to keep a hold of this list and use it when necessary. So if we solve it for A, it'll look like this. VF minus V initial, V final minus V initial divided by T. And there's one other variable we can solve for, and that's T, right? Looks a lot like that one. If we solve it for T, it's T equals VF minus VI over A. A is acceleration, T is time. That's every form of that equation. Right? So we gotta get through doing this to all four of them until we start talking about, well, which equation do I use and when? That gets into specific problems. But at least if you know you have to use this equation, that's every rearranged form of it. All right? I don't care what you guys do. If you guys want to put this all on one page, that's fine. But I'm going to put it on separate pages. It might be nicer to have them all in one spot, just so I could write it nice and big, so everybody could see the best. I'm going to put it on different ones. If you want to just write them side by side and make them a little smaller, that's okay. So that right there is all the possible combinations for equation 1, okay? Equation 2. The original form looks like this. V equals V initial T plus 1/2 AT squared. This one came from some more advanced features of our graph. I'm not going to bore you with the details. But again, like with all of them, it didn't come out of nowhere, okay? Now I'm going to solve this one for some variables that we might need to isolate. So let's first solve for acceleration. Actually, some of these are going to be a little bit, I gotta say, different. There's going to be a lot of times on this one where VI is 0. I'm going to put a little extra thing here. If VI is 0, let me read it like this. If VI is 0 equals 0, the ones I put in this box is only true if VI is 0, okay? I'll put these in a box and use that one. If VI is 0 and we solve for A equals 2D over T squared. A lot of times when we use this one, VI might be 0. That's why I'm doing it. I'm going to make it as simple as possible. If I solve it for T and VI is 0, T ends up equaling the square root of 2D divided by A. Now under this, I'll say if VI is not 0. I'll write it like this. If VI is not equal to 0, that means it's anything else. If we have a non-zero initial velocity in a problem, then these will go for that. So we have some specific circumstance ones here. If VI is not 0, we got this going on. If we solve it for VI, it's going to look, I know, a little ugly. V minus 1/2 AT squared, all divided by T. If we solve for A and VI is non-zero, it's going to be A equals 2 times the quantity V minus V initial T all over T squared. I'll just write this one off to the side. Last option is, well, actually, solving for T when VI is not 0 is not going to be one we do because it gets into some quadratic math that we're not required to do. Okay, so those are all the possible options you might eventually need to use this one for. Just make sure we note that these ones are only if VI is 0. The features one or the other than that. Alright, let's go to equation, the one I called equation 3. And this one looks like this. Actually, this one's not fully solved all by itself totally to begin with. Because if you notice, VF is squared here, right? If I want to get a square off of something, what's the mathematical opposite of a square? Square root. So to solve this one for VF, it's almost already solved for VF. For whatever reason, it's usually given in this form. VF is equal to the square root of all this stuff on the right. There's actually one little other thing we got to do here and be careful with. You may or may not remember this. Somewhere in algebra 1 or algebra 2, when you first ran into the equation, you had to solve by taking a square root. Your answer could be plus or minus. Does anyone remember that? You got to put that there. Because velocities could be positive or negative. Now, which one is it? It depends on the actual problem we're doing. It should be pretty clear when we're doing a real problem. The reason why is when we take a square root, like let's say we plugged all these numbers in from a problem, and we got the square root of like, I don't know, 9, something that has a nice square root, okay? Square root of 9 is what? 3, but it's also what? Oh, we put this here. Could be negative 3, right? Because negative 3 times negative 3 is 9, and 3 times 3 is 9. So mathematically, those two options exist, and physically, when applying this to motion, they exist as well. Because you could have a positive velocity or a negative velocity. We talked about directions on velocity because they're vectors, right? So don't get too worried about that. We'll talk more about it when it comes up in a problem. But for a similar fashion, when we solve for VI, since it's squared, we got to take the square root. VI would equal plus or minus the square root of VF squared minus 2AB. I'm going to flip back a page. You don't have to, but just show something. I didn't really make close mention of it, but when I solved for t in this formula, that t was squared there. This one wasn't around because I said VI was 0 for these ones. Now I did that there, but why didn't I put a plus or minus there? T represents what? T though. Time, right? What kind of numbers can't time ever be? Negative. So that's why I didn't even bother to mention that, right? But velocities are vectors and they could be negative. So we got to leave it open to the possibility when solving that it could be positive or negative. So that's why we put plus or minus. And finally, there might be a need to solve this one for D. If I did that, it would be D equals df squared minus vi squared over 2a. Oh, and I could also solve it for a. There's one more. It looks a lot like this one. It would be a equals df squared minus vi squared all over 2d. So that's every mathematical form of that equation that we might need. And finally, the fourth equation. To give you a little bit of background where this one comes from, it's really the definition of what an average is. It's D equals, let me see, there's different ways to write this one. I do want to be consistent, so I want to go back and look at it like that. They write it like that. I'm going to write it a little differently. It makes more sense. It's the same equation. I'm just going to write it a little bit differently than how it's given. I'm going to put a 1/2 out front instead of over 2. It's going to mean the same thing, but it's more common to see it like this, okay? It's probably easier to use it like this. Even though that's not how it looks like on the original page, I'm going to write it that way. It means the same thing. All right, this equation comes from the idea of an average. When you accelerate, I don't care if you're speeding up or slowing down. Your V initial is different from your V final, right? Like if I'm speeding up, if I'm driving at 30 miles per hour and speed up to 50 miles per hour, my VI and my VF are different, right? And this equation I know doesn't have acceleration in it, but it implies it. It implies it because it changes velocity. There's a different VI than VF. If we add two things together and divide them by 2, or in other words, take it times 1/2, that's the same thing as taking an average of the V's and making it times T. We had an old equation. Don't write this down right now. And just to prove a point, an old equation said V equals V times T. All right? We actually had a V equals V over 2, but that's how you could rearrange it. And this meant average velocity. And the same idea of an average is this whole term right here. So this is just a variation of that one. I'm never going to ask you to prove that, but I just want you to know that there's a place this came from, too, this one as well, that it just didn't come out of thin air. All right, if I solve this one for final velocity, isolate it if I would need to, it's going to be 2d over t minus vi. If I have to solve it for vi, it's going to be 2d over t minus vf, v final. And if I had to solve it for t would equal 2d divided by both of those in addition in parentheses. So that's every possible form of that equation. These four equations, any given one at a time, could handle most acceleration problems, probably all the ones we're going to handle in here. Now, tomorrow I'm going to have a worksheet attached that we're going to work on in class, kind of some of it together, some of it on our own. But the remainder of what we're going to put here today is we're going to be practicing looking at what equation's going to work. So I'm going to write out some problems, okay? I'll make them some pretty short ones. I'm going to use them from a textbook I use in another class, okay? Let's call it example 1 here. I usually don't make you write out problems, but since this isn't on here, I am going to make you write this one out, okay? So the situation is a car travels at 44 meters per second and slows to 22 meters per second over 11 seconds. How far does it move? All right, so here's what we got to do now. We did some basic problems a couple weeks ago and we learned some of the early equations. But now that we're getting into kind of a little bit bigger equations, maybe a little bit more information, we always want to list our givens, okay? If we can't list our givens right, there's no way we're going to pick the right equation. If we don't pick the right equation, there's no way we're going to get the right answer. So our kind of process through all these kind of problems are list your givens, write down the equation you're going to use. We have them all there. They're even rearranged for us. We just got to go back and look at them. It's like solving a puzzle at that point if we get our givens right. And plugging in the numbers, getting the right answer with the right unit, right? So that's kind of everything you have to show. The way I solve the examples is exactly the way I want you guys to do it. Don't skip steps, because if we have a quiz or a test on this stuff, at some point we'll have a little one. You'll miss stuff if you don't show all your work, okay? So, of all those equations we just had, there's 5 total variables. There's only 4 in any one given equation. There's 5 total across it. There's the initial velocity VI, final velocity VF, T time A acceleration, and D distance, okay? And this one, we got to be able to figure out what it's giving us. If we know our units well, we shouldn't mess up our givens. So let's try to think of what variables these givens fall into place. A car travels at 44 meters per second and slows to 22 meters per second. What do you think 44 meters per second is? Is it a final velocity? Is it an initial velocity? Is it a time? Is it a D? Or is it an A? What do you think, Cal? Initial velocity. That's what I'm originally traveling at, right? So you write that down as one of my givens. VI equals 44 meters per second. It slows to 22 meters per second. What is that? Okay. Right, that's the final at some end of some timer interval, which is coming, because we know it, right? So over 11 seconds. Seconds is obviously a unit for time. That's got to be your T, right? If you know your units well, that should guide zero you into what numbers are, even if the wording of the problem is confusing. 11 seconds got to be a time. You can't less than 11 seconds as a distance, right? It's like I traveled a distance of 11 seconds. That wouldn't make any sense, right? Or an acceleration of 11 seconds. 11 seconds is a time unit as long as time. Meters per second are velocity units. Anything in meters per second better be listed as either a VI or a VF. It can't be anything else because that's what it's the unit for. All right. Now, after listing what you know, the next most important part is identifying what it's asking. That can never be really tricky if you're reading it carefully. How far means solve for what? Well, these ones we already got listed. It can't be solved for any of these because we know it. That leaves me with A and D. What is it obviously asking me for? D, right? Okay. Now that I got this, if I get this far, I don't even care if you're terrible at math. This is a matching game. Right? Everybody can play a matching game. Right? We rearranged all four equations. This is why you want to hang on to these. As a matter of fact, what I might do, since you have it on, like, it's hard to write it small and squid and keep it, I'll probably take this same page and carefully write them all out in one small spot so you can have them all at once. But for today, until I do that, we'll just have to flip back pages. All right, where we numbered the equations 1, 2, 3, and 4. Find me the equation that has only those four variables and tell me what number the equation it is. So we got to go back. We'll come back to this screen in a second. Let's go back to wherever you wrote all these down. Let's start here. Remember, VI, VF, P, and D is what we got in my problem, right? Those are my three knowns and my one unknown. I got to find the equation that has those four things, all right? Will equation 1 work? No, because it's missing what? D. D's the primary thing. It better have D because that's what it's asking me for, right? We need the equation, so I don't even have to bother looking at below this. Start with the top one. This is the easiest way to do it. Start with the top. If that top one doesn't have the four variables involved, we go on to the next one. And it's a matching game. Does this one have VI, VF, P, and D? And only those? No, this one has A, and we don't know anything about acceleration, do we? So it can't be that equation. Next one. Does this one have VI, VF, D, and T? No. Almost, right? It almost isn't good enough. Which goes to our fourth equation. This one has all the variables I've identified in my problem, right? So, and luckily enough for this particular problem, it doesn't really matter if it's not the case, but I could actually use the very top formula because it's the one that solved for D, right? Now, if I identified that this was the correct formula, but it wasn't solved for the right variable, I would just look down my list and use the variation that was solved that we just did. Does that make sense to everybody? So we should always look like going across the top equation that I numbered. Find the one that fits, and if it needs to be arranged, then look down the column that we rearranged together and just pop down the right equation. But that first version is the right equation. So the next step, I want you to write that equation down. I don't want you to plug in the numbers yet. This tells me you at least know the right equation to use, okay? After writing down the equation, because that would be worth another point on a quiz, writing it down. Now we plug in, all right? And then we run the math. You could use the calculators on your Chromebook, okay? So I plug in the numbers. D equals 1/2 22 plus 44 times 11. Just to make sure we're all running numbers correctly on our calculator, let's all do that. Grab a calculator, bring it up on your thing now. You could even split screen it if you wanted to, just so you can see everything. And we'll all confirm we get the same value and make sure we get the right unit as well. Anyone get a number answer yet? Take your time. Got anything yet? What do you have? We'll figure out the problem. Yours is right. Okay. And one thing, that's one issue that happens a lot. That sometimes We have all the right stuff up to here and make a calculated mistake. That's correct. All right. Now, we're going to have a division one here soon. Division is where often easy calculated mistakes are made. This one didn't have true division. I guess technically one half. You could consider that. But basically, you could also use 0.5 as a half if you're worrying about cutting a fraction. But as long as you got 363, you're fine. All right. So and once we get the final answer, we got to put the right unit on it. This is a distance, so it has to be in meters, right? Don't put seconds on it. Don't put meters per second. Don't put meters per second squared. We got to know our units. We've learned them all in the past. We just got to remember them now. All right, meters is the core unit we use in here for the Sometimes we do run into kilometers. Sometimes we have to convert, but when that's necessary, we'll worry about that later. All right, so basically what this equation in this application allowed me to do was to figure out how long of a D it would take to slow down in this time frame. All right, and where could that be useful? Many places, especially for like safety features and whatnot. We've all probably seen one thing that comes to mind where you could apply the exact kind of numbers in this problem. And anybody ever been like driving down like a large hill, like elevation, and sometimes they have the runaway truck ramps because like big trucks, they lost their brakes, they're just like dead going down the hill and trying to stop something like that. Those runaway lanes are a certain engineered at a certain D based on what speed limit something's likely going and how long it would take to stop something like that. Equations like this could figure that out, so engineers aren't just guessing. Remember when we said we were watching those videos the other day about dangerous acceleration rates? Remember I said like an engineer just can't say, I'm just going to build this roller coaster, right? And see what it's like. Because if you build it with too high of acceleration, you could kill somebody. And then if you realize that late, that's bad for that reason, but it's also bad for you just wasted a lot of money because you can't ever use that again. So like many of these formulas, this is one of the biggest reasons why physics is such a big thing along with engineering. If you major in any kind of engineering, if somebody that would go do that stuff, you got to take a lot of physics because that's all the science behind it, all the engineering. Having to run all these numbers, yeah, in engineering sometimes you do a little bit of trial and error, but trial and error gets expensive. You know, if you're building something really big, you don't want to trial and error much stuff because if you have to manufacture very expensive pieces and it doesn't work, you want to test it out scientifically. You want to run all the numbers from everything, all the known science, and that's what physics is, and predict what's likely going to happen. You still might run into problems once you actually build it, but at least you have an educated guess and you're close and you don't have to remanufacture stuff. Distances for runways even, equations like this, like when you go to an airport, you know, they didn't just say, oh, well, we're going to just randomly make this runway 1 mile long. All right. Number one, you got to decide what kind of airplanes are going to be there. Like Johnstown Airport is not made for very, very large planes. Right? Their runways aren't big enough. There's a larger plane needs more runway to take off, and it needs more to land. So the style of plane that it's designed for, there's a range of them, I'm sure, not just one type. But they don't just guess of what kind of size runway they need. They take the specs from the plane and decide, okay, this plane needs to get this fast to take off. And once they realize that, know that information, they have to design a runway that provides that length. They don't want to build it way too long because that's just wasting money. No big planes are ever going to be used at this airport. Same with landing. So like that's another like real application of this stuff where it could be used. I know sometimes we run into problems that don't have maybe as much insight as those situations. You wonder why this stuff is necessary, but it all has a lot of applications of stuff we do. All right, let's do another one. I'll kind of let you guys, we'll write it out. I'll let you guys try it a little bit on your own first before we come together and solve it completely. We'll just call this one example 2. That's the whole problem. This is the last one we'll do today. The bus is traveling at 8.4 meters per second. It speeds up at a rate of 3.5 meters per second squared. What velocity does it reach after 6.8 seconds? You guys just take a minute to see what givens you got out of that. And make sure those are right, then we'll let you go and try to find the right equation, alright? Try to pick out the givens yourself. You have 5 possible givens. The I, the F, A, T, and D. What do we think the 8.4 is? Is that an A, T, VI, VF, or V? VI, that's initially, it's in meters per second, it's got to be a V. And that's what I'm originally going at, so that one starts with giving me VI. What about the next number we come upon? 3.5 meters per second squared. Look at that unit. If you remember your units well, you should know what kind of number this is. What variable, what kind of quantity do we say is always in meters per second squared? That can't be a V, because V's are in meters per second, right? Acceleration, very good. Notice something else it says. It doesn't use the word acceleration, but it says speed up, and didn't we learn speeding up is a form of acceleration? It's not using the word acceleration, but basically is because it's saying speed up. So my acceleration is 3.5 meters per second squared. And 6.8, that's an easy one. It's obviously what? Because it's in seconds. That's our what? Time, right? And what is it asking me to find? What's the unknown? Right. At what velocity does it reach? Well, we obviously have initial, so it can't be that. We reach the final velocity. That's what we're looking for. That's the unknown. All right. So after having those, which equation is going to work? 1, 2, 3, or 4? Which fits so good? 1 is correct, and it's actually the first version of it too, right? So we don't even have to go down again. We will eventually have to go down when we do more problems. So it's VF equals VI plus AT. Plug in the numbers and run them. VF equals 8.4. A lot of times what we do in math, you know, when we plug in numbers into equations, we put parentheses around them just to make everything like it's supposed to be grouped together look nice. That's 3.5 times the time is 6.8. We run those numbers correctly and not making any calculating mistakes. I'm getting about 32.3. That's a V, so that's meters per second. That's how fast we should end up going based on all those numbers. Make sense? So basically, if you can pick out the givens, you should be able to get it right. As long as you don't make calculator errors, because then the rest of it's just a batching game of finding that right equation. And I'm always going to let you have that list. Even when I'm not going to make you memorize all those. When you'll have a list given to you that has all those equations on it that you would use to take any quiz on this stuff. Now these are some pretty basic two to start with. Sometimes there's going to be small twists in that. Sometimes you might have to do a conversion. It might give you something in kilometers. We might have to convert to meters. We did that in the first week of school, if you guys remember, right? We did some stuff with that. That's why, because we're going to run into that. We once in a while might have to put a negative on something. You'll see why probably tomorrow. Based on stuff we already talked about, it's just things we got to watch out for. These two were pretty straight up. So we'll stop there today. I'll give you a nicer sheet of these. Just turn this in to the assignment. We got a minute. There you guys go. Just everything we got down here, just submit so you get a couple points for filling this all out, all right?